In a series circuit, resistors are connected one after another, so the same current flows through each resistor. Since there is only one path for current, the total resistance is the sum of the individual resistances. We first find the total resistance of the series combination. Then we use Ohm's law to calculate the current. For the same voltage, increasing total resistance decreases current. For series circuits, the total resistance R equals the sum of individual resistances, R equals R1 plus R2. Then, using Ohm's law, the current I equals the voltage V divided by the total resistance R. Step 1. Calculate the total resistance. Since the resistors are in series, add their values. 10 ohms plus 5 ohms equals 15 ohms. So, total resistance R equals 15 ohms. Step 2. Apply Ohm's law to find the current. Current I equals voltage V divided by resistance R. Substituting the values, 20 volts divided by 15 ohms. Step 3. Perform the division. 20 divided by 15 equals 1.333, which rounds to 1.33 amperes. So, the current I equals 1.33 A. Step 4. Compare with the given options. The calculated current is 1.33 A, but looking at the options, the closest value is 1 A. This is because the options are multiple choice and may not include the exact decimal value. In a series circuit, total resistance is the sum of the individual resistances because the same current flows through all the resistors. Once total resistance is known, power can be calculated using current and resistance. We first find the total resistance of the series combination and then apply the power formula. Power increases with the square of current, so even a small increase in current causes a larger increase in power. For series circuits, total resistance R equals R1 plus R2. The power dissipated P equals current I squared multiplied by total resistance R. Step 1. Find the total resistance of the series circuit. Add the resistances, 4 ohms plus 6 ohms equals 10 ohms. Total resistance R equals 10 ohms. Step 2. Use the power formula P equals I squared times R. Current I is 3 amperes, so I squared is 3 squared which is 9. Multiply by resistance R which is 10 ohms, 9 times 10. Step 3. Perform the multiplication. 9 multiplied by 10 equals 90. Step 4. The power dissipated is 90 watts. So, P equals 90 W. Final answer, the power dissipated in the circuit is 90 watts. In a parallel circuit, the reciprocal of equivalent resistance is equal to the sum of the reciprocals of the individual resistances. Parallel combination always gives a resistance smaller than the smallest branch resistance. We must add the reciprocals first and then take the reciprocal of the final result. If the reciprocal sum becomes 1, then the equivalent resistance is also 1. For parallel circuits, the reciprocal of equivalent resistance equals the sum of the reciprocals of individual resistances. 1 over Req equals 1 over R1 plus 1 over R2 plus 1 over R3. Step 1. Write the equation for parallel resistance. 1 over Req equals 1 over 3 ohms plus 1 over 6 ohms plus 1 over 2 ohms. Step 2. Find a common denominator to add the fractions. Convert each fraction. 1/3 equals 2/6, 1/6 equals 1/6, 1/2 equals 3/6. Adding them, 2/6 plus 1/6 plus 3/6 equals 6/6. Step 3. Simplify the fraction. 6/6 equals 1. So, 1 over Req equals 1. Step 4. Take the reciprocal to find Req. Since 1 over Req equals 1, then Req equals 1 ohm. Final answer, the equivalent resistance of the parallel combination is 1. In a parallel circuit, voltage across each branch is the same. So if we know the voltage across the equivalent combination, that same voltage appears across each resistor. We first find the equivalent resistance of the two parallel resistors and then use Ohm's law to find the voltage across the parallel network. Current may divide in parallel branches, but voltage remains the same across every branch. For two resistors in parallel, equivalent resistance Req equals R1 times R2 divided by R1 plus R2. Then, voltage V equals current I times equivalent resistance Req. Step 1. Calculate the equivalent resistance of the parallel combination. Req equals 5 times 5 divided by 5 plus 5, which is 25 divided by 10, equals 2.5 ohms. Step 2. Use Ohm's law to find the voltage. Voltage V equals current I times Req. Current is 2 amperes, Req is 2.5 ohms, so 2 times 2.5 equals 5 volts. Step 3. Since the resistors are in parallel, the voltage across each branch is the same. So the voltage across each 5 ohm resistor is 5 volts. Final answer, the voltage across each 5 ohm resistor is 5 volts. A capacitor stores energy in the form of an electric field. The stored energy depends on both capacitance and the square of voltage. Since capacitance and voltage are given directly, we substitute them into the energy formula. Energy depends on V2, so increasing voltage has a strong effect on stored energy. The energy stored in a capacitor W equals 1/2 times capacitance C times voltage V squared. Step 1. Write the capacitor energy formula. W equals 1/2 times C times V squared. Step 2. Substitute the values. C is 4 farads, V is 5 volts. First calculate V squared, 5 squared equals 25. Then 0.5 times 4 times 25. Step 3. Perform the multiplication. 0.5 times 4 equals 2. Then 2 times 25 equals 50. Step 4. The energy stored is 50 joules. So, W equals 50 J. Final answer. Inductive reactance is the opposition offered by an inductor to alternating current. It increases when either frequency or inductance increases. We are given frequency and inductance, so we substitute directly into the reactance formula. The factor 2pi converts ordinary frequency into angular frequency. Inductive reactance XL equals 2 times pi times frequency F times inductance L. Step 1. Write the inductive reactance formula. XL equals 2 times pi times frequency times inductance. Step 2. Substitute the values. F is 50 Hz, L is 2 Henries, pi is approximately 3.14. So, 2 times 3.14 times 50 times 2. Step 3. Simplify the calculation. 2 times 3.14 equals 6.28, and 50 times 2 equals 100. So, 6.28 times 100. Step 4. Perform the final multiplication. 6.28 times 100 equals Capacitive reactance is the opposition offered by a capacitor to alternating current. Unlike inductive reactance, it decreases when frequency or capacitance increases. We first convert capacitance from microfarads to farads and then substitute the values into the formula. When frequency increases, capacitive reactance decreases. Capacitive reactance XC equals 1 divided by 2 times pi times frequency F times capacitance C. Step 1. Convert the capacitance to farads. 10 microfarads equals 10 times 10 to the power of negative 6, which equals 0.00001 farads. Step 2. Substitute the values into the formula. XC equals 1 divided by 2 times 3.14 times 50 times 10 to the power of negative 6. Step 3. Calculate the denominator. 2 times 3.14 times 50 equals 314. Then 314 times 10 times 10 to the power of negative 6 equals 0.00314. Step 4. Divide 1 by 0.00314 to get 318.5 ohms approximately, which round. Combination circuits contain both series and parallel parts. The parallel section must be solved first, and then the result is added to the series resistance. The 6 ohm and 3 ohm resistors are in parallel, and their equivalent resistance is then in series with the 4 ohm resistor. The equivalent resistance of a parallel branch is always less than the smallest resistor in that branch. For parallel resistors, equivalent resistance equals R1 times R2 divided by R1 plus R2. Then total resistance total equals series resistance plus equivalent parallel resistance. Step 1. Find the equivalent resistance of the parallel part. Req equals 6 times 3 divided by 6 plus 3, which is 18 divided by 9, equals 2 ohms. Step 2. Add the parallel equivalent resistance to the series resistance. Total resistance equals 4 ohms plus 2 ohms equals 6 ohms. Final answer: the total resistance of the combination circuit is 6 ohms. When voltage and resistance are known, power in a resistor is conveniently found using P equals V2/R. We square the voltage first because the formula depends on V2. For a fixed resistance, power increases with the square of applied voltage. Power P equals voltage V squared divided by resistance R. Step 1. Write the power formula. P equals 220 squared divided by 110. First calculate 220 squared. Step 2. Calculate 220 squared. 220 times 220 equals 48,400. So, 48,400 divided by 110. Step 3. Perform the division. 48,400 divided by 100. Power can also be written in terms of current and resistance. This form is useful when power and resistance are given, but current is unknown. We substitute the known power and resistance and then solve for current. Whenever I2 appears, remember to take the square root at the end. Power P equals current I squared times resistance R. Step 1. Use the power formula. P equals I squared times R. Substitute P equals 80 watts and R equals 20 ohms, 80 equals I squared times 20. Step 2. Isolate I squared. Divide both sides by 20. I squared equals 80 divided by 20, which equals 4. Step 3. Take the square root of both sides. I equals the square root of 4, which equals 2 amperes. Final answer: the current through the circuit is 2 amperes. For resistors in parallel, reciprocals are added. When all resistors are equal, there is also a shortcut. Equivalent resistances are divided by the number of resistors. Because all three resistors are equal, we can use either the reciprocal method or the shortcut. For n equal resistors in parallel, Req equals R/n1 divided by equivalent resistance equals 1 divided by resistance 1 plus 1 divided by resistance 2 plus 1 divided by resistance 3. Step 1. Write the parallel resistance formula. 1 over Req equals 1 over 6 plus 1 over 6 plus 1 over 6. Step 2. Add the fractions. 1/6 plus 1/6 plus 1/6 equals 3/6, which simplifies to 1/2. Step 3. Take the reciprocal to find Req. Since 1 over Req equals 1/2, then Req equals 2 ohms. Final answer: the equivalent resistance of three 6 ohm resistors in parallel is 2 ohms. In a series circuit, the same current flows through every resistor. So the current through the 2 ohm resistor is also 3A. We only need the voltage across one resistor, so we apply Ohm's law directly to that resistor. In series circuits, current stays the same through all components. Voltage V equals current I times resistance R. Step 1. Use Ohm's law. Voltage V equals current I times resistance R. Step 2. Substitute the values. Current is 3 amperes, resistance is 2 ohms. So, 3 times 2. Step 3. Perform the multiplication. 3 times 2 equals 6 volts. So, V equals 6 volts. Final answer, the voltage across the 2 ohm resistor is 6 volts. In a combination circuit, solve the parallel part first and then add the series resistance. This gives the total equivalent resistance seen by the source. The 10 ohm and 20 ohm resistors are in parallel, and their equivalent resistance is then added to the 5 ohm series resistor. Parallel resistance is always less than the smallest resistor in that branch. For parallel resistors, equivalent resistance Req equals R1 times R2 divided by R1 plus R2. Then total resistance R equals Req plus series resistance. Now take the reciprocal to get the actual equivalent resistance. Now calculate, equivalent resistance equals 10x 20, divided by 10 plus 20, equals 200 divided by 30 equals 6.67 ohm. After simplifying the parallel branch into one equivalent resistor, that result lies in series with the remaining resistors, so the resistances add algebraically. Now calculate, total equals 6.67 plus 5 equals 11.67 ohm. Final answer, total equals 11.6. Ohm's law relates voltage, current, and resistance. For a fixed voltage, current increases when resistance decreases. We calculate current for each resistance value separately. Current is inversely proportional to resistance when voltage is constant. Current equals voltage divided by resistance. Now calculate, current equals 100 divided by 20 equals 5A. Now calculate, current equals 100 divided by 10 equals 10A. Now calculate, current changes from 5A to 10A. Final answer, current equals 5A to Power dissipated in a resistor depends on both current and resistance. When current is given, the formula P equals I2R is the most direct one to use. We substitute the known current and resistance directly into the formula. Power rises quickly with current because current is squared in the formula. Power equals current squared R. Since current and resistance are already given, we can use the direct power formula. Now calculate, power equals 4 squared x 5. Since current and resistance are already given, we can use the direct power formula. Now calculate, power equals 16x 5. Since current and resistance are already given, we can use the direct power formula. Now calculate, power equals 80W. Final answer, power equals 80W. Inductive reactance depends on frequency and inductance. If reactance and frequency are known, the formula can be rearranged to find inductance. We first isolate L and then substitute the known values. Rearranging the formula before substitution helps avoid algebra mistakes. Inductive reactance equals 2 pi FL. Inductance equals inductive reactance divided by 2 pi F. The reactance formula is rearranged because inductance is the unknown, so L must be isolated before substituting numbers. Now calculate, inductance equals inductive reactance divided by 2 pi F. Now calculate, inductance equals 314 divided by 2x 3.14x 50. Now calculate, 2x 3.14x 50 equals 314. Now calculate, inductance equal capacitive reactance decreases when capacitance or frequency increases. This means a larger capacitor offers less opposition to AC. We first convert capacitance into farads and then substitute the values into the formula. Increasing capacitance reduces capacitive reactance. Capacitive reactance equals 1 divided by 2 pi Fc. First convert the capacitance into farads. Now calculate, capacitance equals 20 microfarad equals 20 x 10⁶ F. First convert the capacitance into farads. Now calculate, capacitive reactance equals 1 divided by 2x 3.14 x 50 x 20 x 10⁶. First convert the capacitance into farads. Now calculate, 2x 3.14 x 50 x 20 x 10⁶ equals 0.00628. Now substitute the known values into the reactance formula. Now calculate. A capacitor stores energy in the electric field between its plates. The energy depends on capacitance and the square of the voltage. Since capacitance and voltage are given directly, we substitute them into the energy formula. Doubling the voltage makes the stored energy 4 times larger because voltage is squared. W equals 1 divided by 2 CV squared. Now substitute the given values into the energy formula. Now calculate, W equals 0.5x1x 10 squared. Now substitute the given values into the energy formula. Now calculate, W equals 0.5x100. Step 4, the energy stored is 50 joules. So, W equals 50 J. Final answer, the energy stored in the capacitor is in a combination circuit. The parallel section must be solved first and then added to the series resistances. Series resistances add directly because the same current flows through them. The 2 ohm and 4 ohm resistors form the parallel branch, and that equivalent resistance is in series with 3 ohm and 6 ohm. The equivalent resistance of a parallel branch is always less than the smallest resistor in that branch. Equivalent resistance equals resistance 1 x resistance 2 divided by resistance 1 plus resistance 2, total equals resistance 1 plus resistance 2 plus equivalent resistance. Now take the reciprocal to get the actual equivalent resistance. Now calculate, equivalent resistance equals 2x4 divided by 2 plus 4 equals 8 divided by 6 equals 1.33 ohm. After simplifying the parallel branch into one equivalent resistor, that result lies in series with the remaining resistors, so the resistances add algebraically. Now calculate, total equals 3 plus 6 plus 1.33 equals 10.33 ohm. Final answer, total equals 10.33 ohm. Power in a resistor can be expressed in terms of current and resistance. This form is useful when power and resistance are known but current is not. We substitute the known power and resistance and then solve for current. Always isolate I2 first and then take the square root at the end. Power equals current squared R. Now take the square root to find the current. Now calculate, 60 equals current squared x 15. Now take the square root to find the current. Now calculate, current squared equals 4. Step 3, take the square root of both sides. I equals the square root of 4, which equals 2 amperes. Final answer, the current through the circuit is 2 amperes.